So thank you very much. Thank you for the introduction, Fabrice, and thank you very much also for the organizers for inviting me the opportunity to share with you a little bit of the recent work that we have done at the Center for Nanoscience and Nanotechnology, where I work in the group of Jacqueline Bloch. So today I would like to discuss about the recent result that we have on the measurements of topological invariant in a polaritonic analog of graphene, so a honeycomb polaritonic lattice. But before getting started with the details of this work, I'll just give you a brief overview of what we mean by topological invariance. So we have seen many talks this week on topology, but I would like to just introduce this concept of topological invariant that will be at the forefront of this talk in kind of introduction. So in the topological materials, the bands, the electronic bands, or eventually the photonic bands, can be described by a global property that is called a topological invariant. And this property is global because it is defined not point by point inside the band structure, but as a whole. It is an integral over the entire Brillouin zone. So here I give as an example one of the most well-known topological invariant, which is the Chern number. And you can see that, in fact, it is defined as the integral over the entire Brillouin zone of this complicated function that is, in fact, the Berry curvature. And one remarkable property of this integral is that although the integrand can take any kind of value, arbitrary value can continuously be deformed when we modify the lattice. The integral itself, the result, can only take integer value, and the only way to change this integer value is by closing an energy gap and reopening it. And so there is associated to this topological invariant some robustness inside the system. And one of the most well-known examples of robustness are the conductivity plateaus of the quantum Hall effect, which we know can be related to different Chern numbers. And usually we're interested in topology at what happens at the interfaces or at the edges of materials. And the reason for this is that because if you put in contact two materials that are topologically distinct, you need, as I was mentioning, in order to change this topological invariant, to close a gap and reopen it. And this gives rise at the interface of localized states that are robust against perturbation because their properties are not defined by the architecture of the edge, but rather by the entire bulk. All right, so usually in topological physics, we're really much interested at what occurs at the edges. But in this presentation, I would like to go back to the bulk, because as we know, the fundamental properties of topology were originally defined inside the bulk. And what I would like to show is how we can measure this quantity in graphene. And so measuring topological invariance from the bulk without accessing the edges has been done in a variety of systems, including cold atoms, photonic systems, and they rely on a variety of different approaches. Some measurements were done by interferometry measurements to retract somehow the Berry phase accumulated by a particle, a wave packet crossing the Brillouin zone. They have made measurements also on the anomalous displacement of a wave packet that is propagating inside the topological materials. There have also been other interferometry measurements that gain information on the Berry curvature at point by point in the Brillouin zone. However, all of these techniques that were previously elaborated cannot be straightforwardly applied to the case of graphene, because as I will show, in the case of graphene, we have a situation where in fact the topological invariant is not defined over the entire Brillouin zone, but in fact over reduced subspace of the wave functions. So for different cuts of the Brillouin zone, we will have different topological invariants. So there is this complexity for extracting these invariants that needs to be taken into account. And so what I would like to show is how we have elaborated a technique for extracting these invariants in these reduced subspace, and how we have measured them in real polaritonic lattices. And so the outline is really short. I will first show how we can measure topological invariants in a simple 1D lattice. So this is just to benchmark the technique that I want to present and benchmark the technique that we will be using. Then I will turn to the real stuff where we really measure topological invariance in a polaritonic graphene sample. And then I show how we can extend these measurements in a critically compressed graphene sample, where in fact the compression is such that in fact the Dirac cones have merged, so we have a topological phase transition. All right, so the first example that I will be studying is a really well-known topological lattice, the simplest model that exists, which is called the Su-Schrieffer-Heeger model. So it was originally elaborated to describe the polyacetylene molecule here, but all you really need to know about this Hamiltonian is that in fact it describes a bipartite lattice with staggered hopping energies. So all the on-site energies are identical, but the coupling energies alternate between strong and weak coupling. And so we know that for this lattice, we have two possible dimerization that we can define. Either we define it where the strong coupling is inside the unit cell, or the weak coupling is inside the unit cell. And of course, these two dimerization for an infinite lattice are completely equivalent, and the band structure is identical. You see here, you have two bands because you have two atoms per unit cell. They are separated by an energy gap, which is twice the difference in the hopping energies. But what is interesting is that for these two different lattices, in fact, if you calculate the topological invariant, so the integral over the Brillouin zone, for these two kind of dimerization, you will have two different values. So one, which is trivial, gives 0, and one is 1, which is non-trivial. And in fact, if you have a semi-infinite lattice or a finite lattice, and you have an edge, you will see that for the case where you have a winding of 0, you will have no edge states, no states occurring at the edge. But for the other case where you finish the lattice with the weak link, you will have the emergence of edge states at the center of the Brillouin zone. So these are the states that we have used in a previous paper in 2017 to show lasing in these topological edge states. So these are zero-dimensional states that are localized at the edge of this 1D chain. And so in order to emulate this system, what we use is polariton, exciton polaritons. So here you see the building block of what we use to build these lattices. It's a 2D planar cavity grown by molecular beam epitaxy. It consists of two Bragg mirrors encapsulating a cavity in which we include one or few quantum wells. And so in the case where the photonic modes of this cavity enter in resonance with the exotonic mode of the quantum well, in fact, the photon is absorbed and re-emitted and absorbed many times before the photon can leave the cavity. And in this case, the system enters the strong coupling regime, and the eigenstates are no more photons or excitons decoupled, but they form hybrid light-matter quasi-particle called polaritons. And so what we can benefit from these polaritons is both from their photonic part and their excitonic part. From the photonic part, because photons are big particles, we can confine them in synthetic lattice by etching, by patterning these cavities, as I will show in the next slide. But also, since photons are dissipative, they escape the cavity very rapidly, we can image the wave function of polaritons easily using spectroscopy techniques. So we just collect these photons that emerge from the cavity, and we can collect all the information on energy momentum of the polaritons. Also, on the excitonic parts, they give rise to nonlinearities. They are sensitive to magnetic fields, but they also provide spontaneous emission, which will be used in this sample because we're going to have we will rely on driving a system incoherently and looking at the evolution of incoherently generated wave packet. All right, so in order to pattern these lattices, as I was saying, we are using a lithography and etching technique that allows us to pattern these cavities. So here, you see here, this is the building block that we usually use for our lattices, which are these micro pillars that have few microns in diameters. All right, so this is what remains from the cavity inside these pillars. This is what remains of the cavity after the etching. Everything around has been taken out of the system. And so because of the confinement of light in all three dimensions, vertically because of the Bragg mirrors and laterally because of the difference of index of refraction, the eigenmodes of the photons in this pillar are discrete, just like in an atoms. And just because like in an atoms, their different energy states can be associated to atomic orbitals. So the ground state is a S-like orbital. Then we have degenerate P-like orbitals, and so on and so forth. And eventually what we can do is to couple several of these pillars together by simply etching them close enough such that they overlap. And because of the overlap of the wave function, they will hybridize and form molecular photonic modes. So here you see for the two pillar cases, you will have that the hybridization of the ground state give rise to the associated bonding and anti-bonding mode that we usually have in the dimer. And eventually, by coupling more and more of these pillars together, we can fabricate not only molecular orbitals, but also we can find crystal bands. So here I show the case that will be the one that we will be studying in this first part. It's the 1D chain of coupled micropillars. And you can see here on this macroscopy image that the pillars are located close, far, close, far, close, far from each other. So this lattice will emulate the physics of the Schrieffer-Heeger Hamiltonian. And we see this because if we excite the system non-resonantly and we collect light, and that we measure as a function of energy and momentum, which is associated to the angle at which the photon come out of the lattice, we can reconstruct the band structure, the photonic band structure of this lattice, and we really see that we have the two bands that we were expecting separated by the energy gap associated to the Schrieffer-Heeger Hamiltonian. And so, in a first time, what we want to do is to use this simple lattice to measure the topological invariant that I was presented before, and to show how we can do this. And eventually, we'll take this technique for the graphene sample. So the way we do this is that we use a localized excitation on a single pillar of this lattice and a non-resonance, so that much higher energy excitation of one of the lattice. And so this creates incoherently a wave packet that is localized and that was spread over the lattice. And eventually what we do is that we collect light and we image it as a function of space at which it came out. So this is along the chain, and this is the energy. And at the bottom here, what I show is the integrated on energy spectrum. So this is the spectrum of the wave packet that has spread within the lifetime of the polaritons. And so once we have this this intensity profile, we can measure the topological invariance using a technique that was developed from some of our collaborators in the previous theoretical work, which is called the mean chiral displacement. And so this technique of the mean chiral displacement is simply to apply a mathematical operation on this intensity profile that will give us the topological invariant. And the way we do this is that we define an operator called the chiral displacement operator that is given by a product between the unit cell operator, an operator that retrieve the index of the unit cell. So in the central unit cell, it will retrieve 0. Then on the first unit cell on the right, +1, on the left, -1, and so on and so forth. And we multiply this operator by a sublattice operator that gives plus or -1 for the two for the two different sublattices. So below each of these sites of the lattice, I'm showing what is the expectation value of this chiral displacement operator. So we see 0, 0, 1, -1, 2, -2, and on the other end 1, -1, 2, -2. And the idea is that we are going to calculate what's called a mean chiral displacement, which is simply a scalar product between this expectation value and the intensity profile at the specific position. So for each site, we multiply C by the intensity measured on this site. And if we sum over the entire lattice, and with the proper normalization, this, as they have shown in their theoretical work, it will tend toward the winding number, which is here our topological invariant. So we can do this here. So I come back to our experimental data. We have our intensity profile. And here in red and blue, I plot here the value of C. This is the value of this chiral displacement operator. The red and the blue curves correspond to the two different definitions of the unit cell. The blue one corresponds to a unit cell which is defined over a strong link, and the red curve corresponds to a unit cell defined over a weak link. And we see that if we do the scalar product with either the blue or the red line, we achieve that this gives a value which is really close to either 0 in the first case, which is what we expect for a dimerization where we have a strong link inside the unit cell, or almost 1 where we have a strong a unit cell with the weak link. So this is really showing you how we can extract this value of the mean chiral displacement of the topological invariant using this technique of the mean chiral displacement. So now the idea is to extend this technique to a graphene lattice. And we know that there is a really strong connection between graphene and SSH. And one way to really see it intuitively, I would say, is to take a graphene lattice like I'm showing here with a zigzag edge on top and an armchair edge on the side. And if you do now a vertical compression, you completely do a projection and you completely squeeze the lattice on a single line, you will see that all the atoms will fall on a separate position, so that are separated by a weak, short, long links. So you see that there is a connection, but there is a trick here because this small link here is in fact dependent on the value of the momentum. So to really show what is the real connection between graphene and SSH, I would like to just go rapidly through to the mathematics. So this is the Hamiltonian of graphene that is well known, expressed in reciprocal space. So you have 0 on the diagonal because all the atoms in the lattice are identical. Then you have your coupling terms on the off-diagonal term. And if you now define a unit cell that is compatible with the zigzag edge, you can rewrite these terms here just simply by this way. This is just by including the definitions of the unit cell vectors. And what you see in these off-diagonal terms is that you have, in fact, one purely real term here and one complex term here. And so the real term here depends on Kx, and the complex term here is just a coupling strength multiplied by a block term, an exponential of IKy. And so this Hamiltonian is isomorphic, in fact, to the SSH Hamiltonian that I showed earlier, where we have T, which is the intra-cell coupling. So this corresponds to this real part here. And we have an inter-cell coupling here, which corresponds, in fact, to this complex term here. So what it says here is that for each value of Kx here, we have a chain along one that is isomorphic to a SSH. So graphene can be thought of as a succession, a concatenation of different SSH lattice along Y for different values of Kx. And what is interesting is that the intra-cell coupling will depend on Kx. And so for some value of Kx, the intracell will be either stronger or weaker than the intercell coupling. So we will have topological phase transition. So here I'm showing for a zigzag termination. In red, I'm showing regions where this intracell coupling will be stronger, so where the winding number should be expected to be 0. And we see that we are going to alternate between winding of 0, 1, 0. And each time we change, in fact, it corresponds to when the system crosses the Dirac cones, the position of the Dirac cones in the Brillouin zones. So the system closes its energy gap and then reopens and then recloses and reopens. And so this is the evolution of the topological invariant inside the Brillouin zone. So this is really what I was speaking to as when I was saying that this topological invariant now is not defined over the entire Brillouin zone, over one of these hexagons, but on reduced subspaces corresponding to cuts, vertical cuts inside the Brillouin zone. All right. So the idea now would be to measure, as a function of the position in the Brillouin zone, these different invariants. So they have been indirectly measured already using photonic lattices, where people have studied, in fact, the emergence of edge states at the boundaries. But really what we want to do now is to use the technique of the mean chiral displacement to extract it really from the bulk. And so the way we do this is that we are going to do the spectroscopy of our graphene lattice in a very similar way that we do before. So what we do before is that we have our sample, we have a spectrometer split, and in order to image this, if we want to image it in real space, we have two lenses that are here shown in blue, one microscope objective and one focusing lens. So this is just a telescope. It will just image the real space image of the sample on the slit. When we want to do imaging in momentum space, what we do is that we add a third lens at the center here, which is located at the focal distance of the Fourier plane. And what this does is that it images the reciprocal space of the lattice. But the trick part that we're going to do here is that, in fact, this Fourier lens here will not be a normal lens, but it will be a cylindrical lens, meaning that it only has a focal in a direction that is perpendicular to your screen right now. So it will only do imaging in reciprocal space along X, and it will leave the optical rays completely unaffected along the Y direction. And so what this allows you to do is to select a single Kx value with the spectrometer slit, but to still continue imaging all the real space along the orthogonal direction, along Y. And so you are going to have an image that will allow you to reconstruct, to calculate the mean chiral displacement. So as an example, I'm showing here, what do we measure using the setup when we have a position of the cylindrical lens such that the slit of the spectrometer selects a value of Kx equals 0, so at the center of the Brillouin zone. So we see that we have a sorry?
2 minutes.
Okay, that's great. So we see that we have, in fact, a profile that is really similar to what we observe in SSH. So two bands separated by an energy gap. And now we can calculate the value of the mean chiral displacement. So we see that we have a strong value for a definition of the unit cell, where we have a strong link, and we have a very low value for a value defined for a weak link. And so now we don't have exactly 1 and 0 like we were expecting, and this is due to the finite lifetime of the polaritons in the lattice. But now what we can do is to laterally shift the position of the cylindrical lens and recalculate the value of the topological invariance for different position inside the Brillouin zone. And you see that, as I was explaining before, for the two definitions of the unit cell, you really see the evolution from 1 to 0 to 1, and inversely for the other definitions of the Brillouin zone, which corresponds to a birded edge, in fact. And each time these invariance changes is indeed related to the fact where we have the position of these Dirac cones. And so now I would just like to finish by showing these further experiments that we have done, not a normal honeycomb lattice, but in a lattice where we have a uniaxial strain that is applied. And if we come back to the Hamiltonian that I showed earlier, this is similar to putting a perturbation on this T prime here, on this inter-cell coupling. And what is interesting is that if you increase T prime enough by compression, it will be bigger than the inter-cell coupling, regardless of the value of Kx. So here you have a merging of the Dirac cones, because for each value, you never have an inter-cell coupling that could be weaker. And now in this compressed samples, what we're going to have is now that because there is no more Dirac cones, when we calculate the mean chiral displacement, we see that now we don't have any variation of this mean chiral displacement. It's always close to 0 or close to 1, because there is no more phase transition anymore in this lattice. So we really see that we have used this tool not only to probe the invariance in a honeycomb lattice, but also to show the topological phase transition in the critically compressed graphene. So rapidly, I'm going to show my conclusion. So we have shown that how we can extract these invariants in a honeycomb lattice, but also in a critically honeycomb lattice. And this is really interesting, because now we can extract the topological properties of these lattices without relying on the physics of the edge, without relying on an edge, which is sometimes really cumbersome because the edges have disorder, they're ill-defined or whatever. Here we really have a measurements that is extremely precise, and that is from the bulk. And so this could be extended, and we have many perspectives for this, to study the effect of disorder inside the system, how we can induce a topological phase transition with disorder, but we can also try to extend it to other systems that share this chiral symmetry that has the honeycomb lattice, like Lib, Milke, or honeycomb lattice defined on orbital bands, and eventually use the properties of polaritons to study the effect of nonlinearity or eventually non-hermeticity. So I'd just like to thank the people with who I work. So Jacqueline Bloch and Alberto, who supervise this work. I would also like to acknowledge the people who have been working very hard on the fabrication of these samples. Richard for the epitaxy, Luc, Isabelle, and Abdou for the processing, and our collaborators at IFO, Pietro Massigna, and Alexandro. So with this, I would like to thank you for your attention.
Merci, Philippe. Thank you very much for the talk. It's open now for questions, comments, complaints. So we've got one question. Yeah, unmute yourself. I've seen a raised hand in the list. Dimitri, please.
Yes, it's me. Well, thank you very much for this very interesting talk. First, I have a question about this C that you measure. It's a topological invariant or not? It's supposed to be quantized, or it can take continuous values? Especially, yes, on this figure that you show in your conclusions, or yes, or this figure that was just here on the screen, this is smooth curve. It's a smooth of the data, or is the theoretical what you expect theoretically?
So the solid line is the theory, but it's the theory for a system that has a finite lifetime. So C is not an invariant; it's a mathematical operation. And what our collaborators show is that for a Hermitian lattice, this value of C will tend, when we at long enough time, it will tend toward the topological invariance. The problem here is that the system cannot evolve sufficiently long to reach this value of W because of the lifetime of the polaritons. So C does not exactly reach the exact value of W, it reaches a value that is somehow smaller. And if we introduce the value of the lifetime of our polaritons, and now we recalculate the value of C, we see that it gives the blue curve here. And it's really related to what we measure here. But if we were to increase the lifetime of polaritons, this blue curve would become more and more abrupt and more associated to 0, 1, and 0, and 1, and 0.
Yes, I see. And when you said in the conclusions that your method of measuring the topological invariance of the bulk is extremely precise, you were meaning that the agreement between theory and the experiment is good on this figure, That, for example,
yes, exactly.
all
yes, exactly, and that if we were to increase the lifetime of polaritons, then we would have a value that is much closer to the value, because if we come back to the 1D lattice, in this 1D lattice, in fact, the lifetime is an order of magnitude or a little bit less than one order of magnitude longer, and we see that just by gaining this lifetime, now we reach a value that, and there is an uncertainty of about 4 or 5 on this value on the last digit. So you see that you really reach a value that is exactly within the confidence interval, exactly the topological invariance. So this is just, it's not an intrinsic problem. It's really related to the fabrication of these lattices.
Okay,
I see. Well, fabrication, so it means that fabrication can affect the topology.
Yes, because in fact you are probing the evolution of a wave packet, and this evolutions, if you want the wave packet to really reflect chiral symmetry, you need to leave them enough time to kind of distribute it on the different lattice. But if the lifetime is too short to allow this equilibration, then you don't exactly converge to the real value.
Okay, thanks. We've got one question from Olivier Bleu, only to the condition is very fast and fast reply, please, because we are over time. Olivier, please.
Okay.
Okay. Thank you very much for your talk. I have just a small question. You mentioned at the end disorder, but it's not very clear to me how you can define topological invariant in presence of disorder. So could you comment on this?
Yeah. Okay, so this would be a long question, so I'll try to answer very, very rapidly. So it's not obvious, and the idea is that you cannot now do it in momentum space, because K is not defined when you have disorder. But what you can see is that if you can still probe these real space quantities that are defined in real space that are still defined in the presence of disorder, and this has been done. There are some papers I can send you, Olivier, if you want, that have done these for SSH lattices, measurements of the chiral displacement in SSH lattices in the presence of disorder, and to see when the invariant changes from one value to the other. But I can send you some references. But this is a long answer, so maybe this is not the. Don't have
okay, I'm sorry to be rude, but we are really to keep to time, and we are already very much over time. So